So as we already anticipated, we have a sign-up process for the platform. It will be easier for sure if you follow these instructions now, and then send an email to Natalie, who is reading these emails and verify. She will verify you on the spot, so you will be able to join. So I'll show a few slides in order for you to be able to complete the sign-up process, and then we can start the code along in a few minutes. So if you have any questions, please post them. And if I don't see some questions, like, please interrupt me so that I can see them and address them. Today we'll go through a very simple initial setup of a deep learning model that just is a very classical hello world example, so that we can get a feel for what it means to build a model, and then we'll go into a more kind of practical application that will kind of use PyTorch Lightning, the PyTorch Lightning stack behind the scenes to accomplish something end to end. So, having said that, everybody's on sign up. Please remember, when you sign up, you will be told, wait a few hours to be verified. If you write to Natalie at lightning.ai with your username or email, she will be able to unblock you immediately, and you will get free credits for the Lightning platform. All right, PyTorch Lightning. So what is PyTorch Lightning? It's one of the frameworks that was born before 2020, so before this whole Gen AI thing came up. But it's been growing ever since. And essentially, we are updating the slides with the new numbers of downloads. It's been downloaded more than 100 million times. So many companies are using PyTorch Lightning internally. And they do that because PyTorch Lightning addresses one of a few fundamental issues. One is, how do we scale models in a way that is kind of decoupled to the model itself? So how do I go distributed with a lot of data, many parameters, and so on, without requiring me to know a whole deal about writing distributed models and handling distributed sampling, and we'll go into this later. But also it enables collaboration, and so just like the introduction said, it's kind of Ruby on Rails for deep learning, in the sense that it tries to standardize the way you write deep learning models, and in general deep learning code, so the whole iteration and optimization loop, so that if I go into a company that uses PyTorch Lightning, I'm more likely to understand their code and the structure of the code if they're using PyTorch Lightning or not. And I've experienced it in my history. At some point, I had a team that was using heterogeneous ways of writing deep learning models, and then we decided to standardize on PyTorch Lightning before my involvement in PyTorch Lightning directly. And all of a sudden, everybody could read everybody's code. So collaboration is one of the reasons why people and code reuse, why people come to PyTorch Lightning, but then they stay for the scale and so on. So many companies are doing this, and then the case study will do, well, as we say, as we mentioned, create and run a deep learning model, and we'll go about it. So one thing you need to understand if you're getting into AI today, and one thing you for sure if you're into AI already, is that iteration speed is really important. Doesn't matter what you're working on right now. What you should optimize for is, yes, what you're working on right now, and your ability to iterate towards things that require some experimentation. Something new happens, or multiple new things happen every day. And so you need to be able to iterate quickly. And so PyTorch Lightning and Lightning Studios are built to eliminate friction in experimenting and getting to production with new things. Because ultimately, there are many gaps. One is access to compute, collaboration, we already mentioned it. The way you handle data, so you have large amounts of data usually, in AI, and you need a place to store them. You need a way to bring them to machines for compute, and so on. So this adds, for sure, adds some friction. And then how do we handle distributed infrastructure? So if you're a machine learning practitioner and you're doing things that are getting to production grade, more often than not, you will be spending time trying to set up your environments, trying to move your data, trying to figure out how you collaborate with other people, and less in the actual problem itself. So what we're trying to do with PyTorch Lightning and Studios is maximize the time you spend on the value creation part of things and minimize the mistakes that you can make along the way. And so this is how we came up with Studios. Studios, as we will see in a few minutes, is an environment that allows you to, and this is VS Code. It's familiar because it's VS Code, but as you can see on the right side, there's more to it, and on the top, there's more to it. So one of the surfaces of Studios, and the main one right now, is a code editor. You can also choose other code editors like Jupyter. So it's not just VS Code on the cloud, but you need to think about it as a whole environment that is persistent and reproducible. So whatever you do in this environment, like if you install something, it will persist if you switch it off or if you clone it and duplicate it. So you will spend no time in the future trying to move into another machine, because you can change the machine type behind this environment. And since these environments can be ported and reproduced, it makes it easy for me to change the hardware that is running this environment, or to give other people, either publicly or colleagues, a clone of my environment. And we've done it. We've built it so that it feels like using your laptop to have cloud scale compute. And so we tried very hard to not introduce additional abstraction. They're not like just compute, the file system, and so on. And so it's very natural. It's like having a laptop that can scale in compute size, and then I can also duplicate and give to another person while retaining a copy. And the two things now are essentially forked from one another. And so it really enables collaboration and scaling up. So you can do small things a la Colab, Google Colab, or very large things like pre-training LLMs. And it comes with a lot of studio templates, and we'll go into them. Many of the templates are about PyTorch Lightning, which is a framework we'll get into in a second. But it's not, this platform is not dedicated to PyTorch Lightning itself. If you use it, and we'll see this, with PyTorch Lightning, certain things happen magically. Like if you need to go multi-GPU, multi-device, this will just naturally happen. But if you use other frameworks, it will just work because it's just like a laptop on the cloud. And so we have many examples. Some of them use PyTorch Lightning, some of the others don't. And just to complete the picture, we have services that can go from us building models with customers, along with customers, or giving all the pieces for our customers to build on top of Lightning Studios. We have a ton of users already on Studios. We launched them 4 months ago, more or less. All right, so let's go into the application stack. So we'll take a look at Lightning Studios in a second. But where is our open source stack, and what are the pieces that you can use that we maintain on top of everything else that is out there that can be used in Studios, of course. We have PyTorch Lightning, which is a framework to train and deploy any PyTorch model. So LLMs, transformer, vision models, audio, and it will help keeping your code tidy and scalable, and it will give you the ability to scale very easily. Lightning Fabric, which is basically the building blocks of PyTorch Lightning, but exposed. So you have code, you can build things that are much closer to raw PyTorch, but again, you get some of the advantages of using PyTorch Lightning. And this is when you need to have some control on the way you're training the model, you're scaling it up, you're distributing it, some expert level knobs that are available to you that are like more delegated to the framework when you use PyTorch Lightning. And if you're used to framework versus library, I would say that PyTorch Lightning is more of a framework and Lightning Fabric is more of a library. And it's the library that is built to create PyTorch Lightning itself. So using Lightning Fabric, you can build your own trainer, your own private version of PyTorch Lightning that is overfit to your needs. We just released a compiler. It's a first version of our source-to-source compiler. We won't touch upon it here. It's just a compiler that is that is used to speed up, to adopt multiple optimizations together to speed up your models, essentially, and to distribute them again. And then we have LeadGPT, which is a we'll see something about it. It's a code base. It's a library, essentially, that is used to implement certain models, Llama 2, Mistral, many of these LLMs that you hear about, and it allows you to pre-train them, fine-tune them, and serve them really easily. And it uses Lightning Fabric behind the scenes. So it's a very single file implementation, very simple implementation to go through, but it implements all the many of the state-of-the-art techniques that are behind these large language models. Then we have a very popular project that is Torch Metrics that exposes a lot of metrics you can use to understand if your model is doing well or not. And writing correct metrics that behave well at scale is not trivial. And this is what Torch Metrics does. All right, so we're ready to dive in. Anybody has problems signing up on the Lightning Studio platform, just let me know right now, or let Natalie know. All good? Thumbs up? All right. So just I don't want to do an overview, but I want to show you the anatomy and the conceptual look of what PyTorch Lightning is. PyTorch Lightning does not wrap, it's not like Keras for PyTorch. It does not wrap PyTorch itself. You still write your model in pure PyTorch. It just facilitates and organizes the way you split your code, your training code, into a training step, which is where you run your data through your model and then return what is called the loss, which is the objective you're trying to optimize. In this case, it's the difference between the quadratic difference between an input and what the expected output should be. And then it returns it. And then it lets you choose what optimizer to use in order to optimize the weights of the model. So what the parameters of this model that will lead it to have a different output. So every model has a few parameters, like, for example, in this case, you have a linear module, which means I have an input and then I multiply by a big matrix and I get an output that is the result of that matrix multiplication, eventually with the addition of a constant, which is a bias, another vector, which is called bias. And both the weights of the linear layer, so the matrix multiplication and the addition component, are parameters that are initialized randomly, usually at the beginning of training, and that are the whole point. So you keep sending inputs into the model, evaluating what the effect, what the loss is. So what is the error that we're making in predicting the input given known outputs, and then the optimization process will change these weights and these biases in order to have this error essentially decrease over time. And so if the error goes during the optimization process, the error goes down, you will have a model that in its weights encodes some knowledge, which is the knowledge of how the inputs map into the expected outputs, essentially. And this optimization process is what happens here in the configure optimizers. So you have this class where you have all the life cycle of what needs to happen to the model now in order to be trained. And then you pass this Lightning module, into a trainer. And the trainer is the engine that will take this Lightning module and do this optimization loop. So the optimization loop essentially is calling all these hooks. We call them hooks. They're just methods in the Lightning module that the user needs to implement. And it will call them at the right time. And if it's distributed, it will call them again at the right time and do the right things so that during this call to fit, the weights of the model are optimized. So this is like from a mile up, and we'll go practical right now and do it from scratch. The nice thing about PyTorch Lightning is that once you define this Lightning module with all the lifecycle hooks defined, properly defined, then passing new arguments, new options to the trainer will give your training loop a new properties. For example, if I want now to run on 4 devices on the GPU, so instead of running the same model on the CPU, then the trainer will know, since you organize the code in the Lightning module already, will know what to call in order for the model to be transferred to the GPU and distributed across 4 devices. And then we won't have a lot of time to get into the details of distributed, but there are many strategies to distribute the computation across GPUs, for example. One is I keep 1 copy of the same model across all GPUs. And so this means that each GPU need to be able to host all the weights of that model in its memory. And sometimes this is not possible. So I use multiple GPUs, and each of the GPUs keeps a chunk, a shard of the model to be optimized together. And this is what DeepSpeed or FSDP do. And so I can specify the strategy, and the trainer will know how to configure the model in order for the computation to be distributed, right? But I don't have to change the training code. It's just a configuration on the trainer. And this is what, like, decoupling the what from the how is one of the convenient things about PyTorch Lightning. And then, like, I can set how many epochs. An epoch is me going through all the training samples. And so 1 epoch is when I finish looking at all the data I have to and optimize through all of that. And then I can repeat the process multiple times, and this is called an epoch. So I can specify how many epochs and so on. And I also have the concept of a callback, which is basically a callback is a set of hooks that I like take out, and then I can import, so that at this point the hooks defined on the callback kind of override some hooks that I might not have defined in the Lightning module. So I can kind of import functionality. So we spoke to companies that it's kind of usual for companies to have registries of callbacks that they use privately to, for example, log things or to do evaluations of models and so on. And so they can standardize the way they work independently of the model they use. All right, so I will stop talking over slides at this point, and I will just go and kick off our live session. So everything I said up until now, you can find in the docs. So the docs are the place to go. You find the PyTorch Lightning docs here, and there's a Lightning in 15 minutes that will kind of take you along what I just described. But we will do something practical right now by coding live as well. So just head to the docs if you want to dive deeper. All right. So if you didn't sign up, this is the homepage that you will see. And this is Lightning Studios. It will kind of tell you what you can do with it. Of course, you can build, go from like data prep to training to deployment, and our nice homepage will show you all that. So you should start and sign up at this point. I'm assuming that you guys are signed up and in the platform already. And so we can just go ahead and start a new studio. Okay, so a studio, yep.
Luca, sorry to interrupt you, but can we just adjust the zoom just so we can make sure those with a bit tired eyes like myself can see the code. Thank you so much. But that's
Is that
it.
enough?
Yeah, all good. Thank you so much.
Yeah, thank you.
Yeah, awesome.
I'll zoom out one notch. Okay, great. So I think this is a good balance between things. All right, so I'm entering an environment that is setting up for me. This is a machine on the cloud, and I have the whole environment at my disposal. You could see the icon here that turned from yellow, which is I'm getting you the machine, to green, you have the machine. And now this environment has been initialized. And for now, it's just a plain main.py. I can just run it for the sake of it to check that everything is working for me. The first time is maybe a bit slower. Yeah, okay, because it needs to load the environment. All right. So as you can see, nothing to see here. Actually, this is the whole machine. So I open the terminal down here, and I can even apt or sudo apt install. I don't know, what could it be? Vim, I think it's already installed, but you know, you can do stuff like that. So you have full control. It's not a shim of a machine, it's actually a whole machine. All right. You have other things here that you can see. So I think they're interesting. One is terminal. You can open a web terminal. We just use the one at the bottom from VS Code. They're exactly the same thing. So I will find the same things in both. I can see the same files and operate in Jupyter. I'm not a Jupyter guy per se. I prefer a code editor, but if you like Jupyter, you can follow along using Jupyter as an editor. It's just a personal preference. And then we'll look at these plugins later. You also have a drive view. The drive allows you to see whatever you have in a global file system that is associated with your account. Actually, it's associated with something called team space, and a team space is basically a workspace, and you can have multiple of them. And in a workspace, in a team space, you can have multiple people join, and they will kind of share with you everything that you do. And in fact, I was kind of running through some examples before, and in this team space, I have a few studios, and even if the studios are shut off, I can still see their content and their code and so on. So I have full access to their file system. And when speaking about file systems, I can also add data here. If I have external data, I can attach an S3 bucket, and this will be mounted on top of every studio in this team space. And if it's a private one, I can still attach a private one. We just give you the bucket policy to attach to specify on the AWS console side so that this becomes available. We can just, for the sake of it, say ImageNet tiny. And this is a public one that we created. And this will be attached immediately, and we will start making the files that are available on the Steam space accessible to you. And as you can see, we can browse gigabytes of data in real time because it's all based on optimizations that we do to make it available in real time. And not only you will have it here, but if we go back to the studio here, I can open a new terminal, and then I have a mount point here called team space. And in this team space, I can see the other studio file systems. This studio is called this studio without a lot of fantasy. And then We have, for example, instruction tool llama, and I can access other studios. I can access them read-only and not read-write to make sure I cannot mess with other people's work. But then it becomes really easy to say, okay, I'm starting a studio for a specific purpose. I'm saving a checkpoint there, and then a colleague of mine will be able to read that checkpoint in their own workflow, and either read it or copy it, and so on. About the S3 connections, I have the ImageNet Tiny that is being loaded here. And so every studio at this point will have ImageNet that you can use as to get data, private data to studios and so on. All right, private or public data. Okay, so HStudio comes with a few packages pre-installed. I can use, well, of course, I could use apt install anything, so I can also use pip. But if we see, like, if we go into Python and import Lightning, Lightning comes pre-installed here. There are packages that don't come pre-installed. I think XGBoost probably doesn't. Exactly, there's no XGBoost. Sorry. Let's, hide. How convenient. Yeah, I click hide, but it's not actually hiding, so it's broken promise. Okay, great. XGBoost is not installed here, so I can just pip install it. And I'm installing it because I want to demonstrate that when you then duplicate or jump to another machine type, this environment will be preserved. And this is very important because you don't have to mess with creating Docker files and so on. Everything you do here is in a reproducible environment at the point where I'm at right now. So if I switch it on, or if I go to an instance that has GPUs, for example, and I can do that here, very exciting, we have a new L4 GPU type. You can also jump on machines that have more than one GPU. We'll see that this in a few minutes. But essentially, I can just jump on one random one. Let's see, the T4. And what's happening here is that I'm now requesting this studio to run on a T4 machine. And I can jump on the T4 machine and we can start coding from there. Yeah. And here, without changing my surface, essentially the T4 machine is already powering the studio. And so one typical thing you will do is to code on the CPU studio and then jump on GPU when you want to run something important and then go back. The fact that you get a free CPU studio all the time, so you can code, and then you get 15 credits renewing every month, but you can use them when you need them, and the billing is happening by the second, means that those 15 credits, if you use them judiciously, will last for quite a long time, because you don't need to code on the GPU machine. You can just run stuff when you need it and verify stuff on the GPU machine. So here, if we go to Python and we import Torch, and we ask if Torch CUDA is available, it says true, because in fact, we have a GPU here, essentially. And so now I switch to a GPU environment. Okay, let's go back to the CPU and code there, and then we'll come back to the GPU to kind of demonstrate that everything worked for us. And we can run faster on the GPU. All right, so the example I want to run through is a very simple example, as kind of as it was mentioned, the hello world for deep learning, which is digit classification. It's very uneventful as an example, but I think it's simple enough that everybody, even the ones of you who are not into AI today can follow along and kind of understand the principles, and then we can scale up to something different. All right. So, are there any questions up until now? Can we start coding?
So we have a couple of questions.
Yep.
This one is from AO Wow Wow. So AO Wow Wow, is there a way to see the end result in case the callback overwrites something?
The end result, well, of course, as you will see, usually when you save checkpoints, for example, you will save them, and every time you run a new experiment or rerun the thing, it will automatically create a new directory where it will save intermediate results. So typically you don't override, but of course, if you specify like hard code the same path, it will kind of override it. So.
Okay. That's awesome. And then we had a couple of other questions as well related to the sign up, but I think we already addressed them in the chat. So I think, yeah, you're good to go, Luca.
All right, let's go. All right, import Lightning as L. Okay, so one disclaimer. Lightning for us is the package that contains everything. So you have PyTorch Lightning, you have Fabric, and so on, and maybe you will have more things and some other packages that are coming down the road. But if you want to have fewer dependencies, you can also pip install PyTorch _lightning, or is it PyTorch -lightning? I never remember one or two because I always use the other one, and also Lightning Fabric. So if you go to pypy.org, you can see PyTorch Lightning. Here it's dash. And this will only get you PyTorch Lightning. So if you're worried about packages that are too large, it's not very large. Like the Lightning package is still not very large, but if you just want to have this or Lightning Fabric, you can also just install Lightning Fabric and you won't get PyTorch Lightning. For those of you who are starting and don't know exactly what you're going to use, then we have the Lightning package that we usually have this incantation for, import Lightning as L, and that will expose the whole stack. So I suggest you start with this if you don't know what you're doing, and then if you want to do kind of go more with a more parsimonious approach, you can switch to the other, and they're completely compatible. They're actually the exact same code, but packaged differently. One is in pieces and one is the whole thing. All right. Just as a clarification, because I get this question a lot, like, what is Lightning? How is it different from PyTorch Lightning? Lightning for us is just the package that with which you get the bundle. It's a bundle, essentially. All right. Yeah, so the first thing to do, I think, is create a model. So let's create this model, or maybe get the data. Let's get the data first. We mentioned that we want to classify digits, and this digit classification thing is contained in the MNIST dataset. You probably have seen it multiple times, but this is the MNIST dataset. Do you know where it comes from? It comes from NIST, and NIST is an organization that had to do, in the 80s, I think, had to do classification of the digits written on checks. So as these controls were automated, instead of people saying, oh, this is a 47A32 account number, or how many dollars you want to this check contains, they wanted to develop something that would understand the individual digits. And so they built this data set that for the time was very large. And Jan LeCun worked on this directly at that institute. And this is where these data sets come from. And of course, at the time there were multiple approaches, like, for example, see if it's a circle, see how long it is, extract features here and there. But then it was the first example where a deep network, or not so deep network at the time, could recognize digits and classify them no matter what their shape was, in a pretty interesting way for the time. And this is where it all started, essentially. Oh, sorry, it was 94, not 80s, in the 90s. Yeah, of course. All right. So this dataset is contained in the Torch Vision package, which is also pre-installed. So let's check that it is pre-installed. Yeah, it is pre-installed. And this has a few things in it, and one of the things is datasets. So it comes with typical datasets for vision, and one of the small ones is MNIST. Another fun one is fashion MNIST, which is like little clothes and so on, which is here. That has the same characteristics like the image size as MNIST. That makes things a bit more interesting. But let's import Torch Vision datasets, and then we'll need something more, but we can introduce it later. And we have this section here, and then we can do the loading of the data using training datasets, MNIST. We can set a root folder, which is going to be, I don't know, MNIST in the home. And then we want the training set of this dataset. And then we can ask it to download it directly. And one of the things, okay, let's first run this. All right. Okay, so the dataset has been downloaded. We can see it here, and it will appear also on the datasets folder in the drive, of course. Okay, so these are unsigned bytes. So they're basically all the images one after the other. All right, but it would be nice to take a look at them. So one way we can do that is by just get, well, first of all, let's see how many of them there are. Okay, this has been cached, so you shouldn't download them again. Okay, there are 60,000 of them. We can try to get one. So PyTorch dataset is something you can index, essentially. It behaves like a list, a Python list. Oh, sorry. Right. All right, it's a pill image, which is nice because now if we do, let's create another file, or you know what we can do is convert this to Python notebook. All right, so let's port the imports here so we can view the images there. We can just start a notebook. It's really convenient to run notebooks in VS Code, actually. It's something I like to do because I can then switch back. Okay, and then we can just load and do the exact same as we were doing before. Print the image, and the pill image has the ability. Actually, it's an image and sorry, it's a pair. It's the PyTorch dataset comes with the sample and the target, and here there is the image and then the 5, which is the class. So what we can do is get the first of the two, or we can unpack the two. Right? Great. And then we can just say show. And this is a 5. That's very badly written 5. And target, of course, is what we expect it to be. Right. Okay, so we now understand that these data sets come in. What is the input to a model? And I don't know what the model is right now. And then what is the target in terms of like what I want the output to be once my model, whatever it is, processes these pixels. All right, so now we can go back and write a nice model for it. So one of the classical models that I can write is called multi-layer perceptron, MLP. So let's do something like this, plus MLP, and I'll explain you in a second what this is. Sorry, one sec. It's a presentation. Sorry, one sec. All right, and module. Okay, a model is a PyTorch NN module usually. So it's a class. It's a Python class that has certain properties. Like as we said before, if I use a linear module, it will take the input multiplied by something, and that something is a set of parameters that the model has, and it needs to optimize. So a torch NN module is something that has a machinery through which every layer I initialize in this model, every component of the model gets registered in the torch NN module. So the torch NN modules will know what are the parameters that I need to optimize. So this is the magic that happens behind the scenes. So what I need to do here is have a constructor, which is where this registration will happen. Sorry. We'll write kind of a generic classifier here. And of course, we need to call the parent in it. And then we'll say, okay, what are the layers of this model? All right. So one way of building a model, which is a stack of things, like, for example, if I go to MLP neural net, this is the, sorry, I was looking for an image that you can also get. This is exactly what I'm looking for. So I have layers and I need to build, I have input values, they will be multiplied or something. And then the output will feed into another layer and then will feed into another layer until the output. So a sequential module will allow me to stack multiple of these together. And as you can see, I'm not writing PyTorch Lightning right now. I'm just writing raw PyTorch. So the sequential module is something that is a container, is like a list of modules. And in these modules, I can say, okay, I'm gonna have a linear layer, a linear layer with a certain set of features in input, which are how many numbers my data has that I'm getting with and then how many numbers I want this representation to have. So I go from one representation, which is the images, to an output representation of that linear layer that have another set of numbers. And these are the intermediate features. And then I can stack another one. And then I can stack another one. All right. So if I stack many of these and I stack linear layers one after the other, the point is that a linear transformation of an input followed by another linear transformation and another linear transformation, and linear, as we already touched upon, it's just a multiplication and addition, can be expressed as a single linear. So this is not very expressive, it's actually very wasteful. So the trick for neural networks to to work is to insert some nonlinear function in between the linear layers, so that the computation can assume nonlinear behavior. So it can represent a richer set of functions and not just linear functions. And I can do that with pretty simple functions like ReLU, for example, is just a linear, like x equal, y equals x, except that it's only valid when x is positive. So if the input is positive, it will return me the same number. If the input is negative, it will return 0. So it basically strangles the computation at whenever it sees a negative value. And this is enough to allow the model to represent complex functions. And this is the key to give expressiveness to the model. And we'll keep the output without a nonlinearity after it. All right, so this is our model, the definition of our model, and the way I call it is by defining a forward function to it. I will start. Okay, I will set a tensor in input. I will straighten out, this is what flatten does, the image in input into a set of numbers. So all the pixels will be read from left to right up until the end in a long set of values. Usually vision models have a more sophisticated way to go about it, but this already works. And then I can just go, pass this input through all my layers here, and then obtain something called logits, which are kind of the output of this model, and then just return them. I can just return the output essentially. Okay, we have the model. How do we train this model? How do we make the magic happen so that all these linear modules tune their weights, their internal matrices, so that the output is the actual correct one? Because right now there's nothing that taught this model that image, that 5 image, should come out with a 5 on the other end, right? So the way we do it is we define a Lightning module where I can define all the lifecycle hooks that will allow this model to train. Okay, so super init. So we have something called learning rate that dictates how quickly my model needs to learn. If it's too quick, it will not converge. If it's too slow, we will get a while to get there. So usually this is a very important parameter to tune, and we'll touch upon it in a second. And then we have a model that we can pass in. Of course, a Lightning module is also a child of Torch and N module. And this also allows me to define all this sequential model directly in here if I want to. In this case, we will just pass it as an argument. You can do both things just to keep things simpler. What I need to do is define a hook called training step. And I'm expecting, in this training step, I'm expecting a batch of images and a batch of targets, so that I can compute the error between the two. So let's say the images are here. I call them features because they're not really the images, they're kind of straightened out. And then labels. And then I can compute what we called logits before. And just have features here as an input to the model, right? So we define the model, we pass the model here, and then we say, okay, this will be called at some point because it's a framework, right? So we know that at some point this hook will be called training step, and I need to define what will happen when this method will be called. And the expectation here is that I'm coming with a batch of data, which is a collection of images that have been straightened out, and I need to pass them to the model so that the forward method of the model will be called and the output will be generated. Of course, the first iteration of this will produce nonsensical output, but this is not the point. The point is that this will allow me to define a measure of error. And a very common one is a cross entropy between the classes, the probability or the logits associated to each class, and what is the right class instead. And then the cross entropy between the logits and the labels, the true labels. And so this is a measure of an error. And I need to return this error. And this will be the error that gets returned so that PyTorch Lightning says, okay, this is the error. I can call some methods on this value that will allow to inform the model on how it should change its parameters. And the thing that will actually change the parameters is called the optimizer. And so I need to define, as a minimum, I need to define the optimizer. There are many of them. The most simple one is stochastic gradient descent. There's another one called Adam, which is very used because it's less sensitive to the learning rate. Something I need to define here is basically the parameters. So I can pass the parameters, and this will, since we assign model here, and since this is a torch and end module, my Lightning module will already know that these calling parameters will go into this and pick out all the parameters that need to be optimized during the optimization process. And then the learning rate, which is another argument that we need to pass, that will pass from the outside, is also passed here. Okay, and then I can just return. All right, we're done. So this is a very minimal example, but it's kind of like whatever is needed to train a model. All right, so let's define the model here. And I don't remember, it's MLP with a number of features. The number of features is basically these are 28 by 28. So if I straighten them out, they will be 784 numbers, right? Because 28 by 28, if I straighten it out, I have a long vector of 784 features that are my input features. And then how many classes I have? There are 10 classes because it's the numbers between 0 and 9. All right. So I have my model here. I now need to define the Lightning module, which is my classifier. And in my classifier, I can pass my model. And again, I could define my model directly in the Lightning module, and you will see many, many examples of this. And then the learning rate, it needs to be a small number, and you will be able to tune it yourself. And all I need to do now, as we have seen in the first slide, was to define a trainer. And the trainer is whatever is the machinery that I will not subclass, I will just instantiate it. And I will pass my Lightning module with all the hooks defined so that it can then just optimize it. All right, so let's define the trainer. I will run through all the examples 10 times, and that's it. And then I will just say trainer.fit, and I will pass the Lightning module in there, and I will also pass the training data loader. And the data loader is something I need to define. 1 second. Okay, I have the data set. I need to do another thing, which is transform it to a tensor. Because right now the data in the data set is made of pill images. Pill images are not really things you can run PyTorch Lightning code on or PyTorch code on. You need to turn them into PyTorch tensors, which are the basic building block, the basic data of PyTorch. Like if I do torch and I say, I don't know, tensor, and I do this, I will have a tensor object. Whoops, sorry. And this is what a tensor is. Essentially, it's a collection of numbers of any dimension. So my images, I need to turn them into a tensor so that I can manipulate them. And Torch Vision comes with this transforms module, and the transform module allow me to turn whatever, like to specify transforms from the data, that the raw data type that arrives from the data set and then goes through a pipeline of transformations. And I can do many things like augment them, rotate them. I can do many things here. But the basic one is turn them into a tensor. So let's limit ourselves to turning them into a tensor. And once that's done, I need something that will load the data sequentially. And that is called the data loader. So it's the data loader is in, sorry, let me add this here, otherwise it's noise. Torch utils, data import data loader. That's great. And so the data loader is something that is independent of the data itself. It takes a data set like this, and then it will let me specify how many samples I want to load at a time. And this is because it's really important for hardware to be fully utilized. So this is very small data, and if I ran the optimization process on one sample at a time, it will take me a long time to go through all the 60,000 samples, and probably my CPU or even worse, my GPU will be fully non-utilized. So what I can do is I can increase the batch size, which means how many samples I just vectorize my computations on, so that I can just process 64 at a time. And so I will see my GPU or CPU to be more utilized there. And I can also choose to load data in a shuffled way. So I inject randomness in the process. Right, I have my train loader, and so I can pass it as a train loader. So you see what's happening. So the trainer is something configurable, and then in the fit, I can pass the model and the data loaders, and the trainer will take care of running the training loop for me. And so all I did is define a pure PyTorch module, so no wrappers. Define all the moments in time where I run my, so how my optimization process will happen, what kind of loss I'm evaluating on, and what will drive the optimization process, and then the optimizer itself. And this is enough for us to run the optimization. So let's see if this works at all, or if I made stupid mistakes in the meantime. Yeah, for sure. Where is it? Relu. It's here. Sorry. Oh, sorry. Import torch functional as F. All right. So the training process is happening, meaning that the CPU itself. So I'm not using a GPU here, but I'm already at the second epoch. So I already processed 60,000 examples. And as the training goes on, the optimizer is called, and we can actually plot the accuracy or the loss. I have something here called events. So I have Lightning logs. I have multiple versions, which is all the times I launch this, there's a new version. So to the question before, every time I launch a training process, PyTorch Lightning will make sure that it creates a new version. New version of what? New version of everything it's recording. So one is, well, I can optionally record all the parameters I called it with, like, for example, learning rate. I have events, TensorBoard events. TensorBoard is a tool that you can use to track your training, and I'll show you in a second. But it looks kind of like this, and we ship it within Studios automatically, so I can just start this TensorBoard. And it will get whatever TensorBoard events are in the studio. Oh yeah, because I need to launch TensorBoard here. So or TensorBoard log there, and I can pass Lightning logs version 1. All right, and I can go here, and it should show me the. Whoops, what's going on? Sorry, guys. That's unexpected. It's probably doing something not right. Yeah, I wanted to show the shortcut from here, but actually it's actually better to. Oh yeah, that's why I didn't record the TensorBoard logger. So I don't understand why this was not picked up. Anyway, let's shortcut this and let's move on. I think we don't have a lot of time, right?
Yeah, so we are a few minutes over time. Maybe look if we can do just like that.
Yeah.
Can you hear me now?
Yep.
Yeah, so we are running a bit of time. If we can maybe wrap up that final kind of training task, and then I think we can take a couple of questions, and then we're good to go.
Yeah, great. So yeah, about the training task, you will see checkpoints here. These are checkpoints. These are files that you can load back into PyTorch Lightning. You can see in the on the docs how you do it, and this will allow you to either resume training or load the model to do further evaluation on it. For example, we don't have a lot of time to go through the accuracy of the model. But essentially, after this fit, we could load the validation set, for example. And I won't do the whole thing because there's no time. But you can say, you can load the train false version of this. And so this is the non-training data set. And you can do exactly the same as we've done before. And you can run some validation on this data loader. So you can just iterate over these samples and see if the class that is predicted is the same. Like, for example, for index in features labels in enumerate val loader, you can have logits output from the model. So you can input the features of this data set coming from the validation loader. and then just do what the prediction is. So the maximum logit will tell you what is the class that was selected. And then you can say, okay, the comparison is the label equal to the prediction? It's actually, or you can count how many of them, and like, for example, you have a comparison. And then you can say, okay, how many correct did I get? And then say, okay, over this set, I can initialize correct here. And over the set, I can just say, okay, what is in the batch? Actually, this is a batch, so sorry, logits. These are predictions in the batch, and I have labels and predictions, and I count how many of them are the same, and I sum all the ones that are the same because they will be equal to true, so logical 1, and I can count how many correct ones, and so I can return the ratio of correct, or sorry, I can print the correct over the total examples, and the total examples I can just compute them here. And it will be lag compare. All right. So this will allow me to evaluate, and I can do this in the Lightning module as well. So I'll leave this as an exercise, or I can use torch metrics. That is a package that will allow me to compute all these accuracy measurements and so on. So from here, you can experiment with different learning rates and so on, and different optimizers. And these are like kind of completes the general view. Another thing you can do is actually log the loss at every step, and the simplest thing to do here is just log training loss and loss, and this will make it appear on the TensorBoard dashboard. And I forgot to do that, and that's why it didn't happen. But the Lightning module has a way to kind of log things properly. This seems like a simple thing. When you go distributed, then logging properly becomes also a bit of a thing you need to think about. So PyTorch Lightning will take care of logging distributed. How do you go distributed? It's really easy. You can just switch to a multi-GPU instance here, and you run the exact same code, and it will go distributed, because here there's a default devices auto, and it will auto detect how many devices you have on your machine, and will just run it on the right device, so GPU, multiple of them, right? And if I launch this, it will just run distributed. And so this is the power of having something like Studio together with something like Lightning, means that I can just care about writing the serial code, and it will just make it distributed for me. Making it distributed means that large trainings will happen faster, right? And I can just run this. I switched to 4 GPUs now, 4 T4s. I detected there are 4 GPUs, and it's initializing the distributed computation, and you see how fast this goes. It's just super fast. Of course, this is a very small example, and I wouldn't need 4 GPUs and so on, but the same principle can be applied to larger models. And just to close out here, we have a lot of templates that you can look at that go from pre-training large language models to fine-tuning large language models. Fine-tuning means you have a pre-trained model, you want to kind of tune it to your needs, to your small data set. So you kind of tune the behavior of the model or make it learn new things. And we have things in the image domain and audio domain. You're more than welcome to come and look at the public templates. We have studios that allow you to run a very large model and expose it through an API and so on. So you can go from grabbing data, scraping data from the web, to pre-training your model, to deploying your model, evaluating how good it is, and then expose APIs. And there will be many more features that I can highlight in eventually future talks that I'll give around. All right, so I think we're done. We're more than encourage you to try things out yourself, get to coding, get the basics, and then upscale yourself to do more complicated things with these templates.
Luca, that was awesome. Highly recommend that everyone checks out, the templates shared here. We have received a couple of questions, but unfortunately, we won't be able to get to them due to time constraint. What I recommend for everyone who had questions, do reach out to Luca directly on LinkedIn. You can access his LinkedIn directly in the event on LinkedIn if you're there. We'll also be sharing in the recording as well. I wanted to say a huge thank you for everyone who joined us today for this code along, and a huge thank you for Luca as well for sharing all of his great insight and showing us the PyTorch Lightning package.
Great. Thanks so much for having us here.
Awesome. Have a good